So for this, we use the formation enthalpies that I've reproduced over here. It's just the enthalpy of the products times their coefficients minus the enthalpy of the reactants, because delta is always sort of finest minus initial, so products minus reactants. The equation for that is something like this written out here, but sometimes that just confuses people. All you really need to remember is that it's products minus reactants. So in this case, my product's 3 CO2, so 3 times negative 393.5 plus 4 H2O. It's as a gas, so I need the gas enthalpy, so 4 times negative 241.8 minus, and then my reactants are C3H8, just one of those, so minus negative 103.85 plus my 5O2, but remember O2 isn't shown here. That's because elements in their standard states have an enthalpy of formation of 0. So O2 gas has an enthalpy of formation of 0. So this is sort of 5 times 0 here. And when you go through and do that math, you get delta H naught is equal to negative 1256.8 kilojoules per mole is delta H naught for this reaction. So this question uses that calorimetry equation, that equation that relates heat, mass, and specific heat capacity here. So Q, remember that's the heat in units of joules. M is the mass in kilograms. CS is the specific heat capacity. That's the how much heat per gram of substance you have, so specific heat capacity. And then delta T, again, is the change in temperature. So this is the final temperature minus the initial temperature. And so the key parameter here, the specific heat capacity, to absorb the least amount of heat, you need the smallest heat capacity. And so in this case, that's iron here has that lowest specific heat capacity. And so the amount of heat it would absorb, just plug into the equation. Q is equal to 100 grams times 0.444 joules per gram degree Celsius times, we're heating to 70, so 70 degrees Celsius minus 25 degrees Celsius. And when you multiply that out, you get the amount of heat, which is 2,000 joules, or 2.0 kilojoules. It's always important to check the sign here. So in this case, this thing got warmer, absorbed heat. That's reflected in the fact that Q is a positive number. So in part B here, now we have a fixed amount of heat, Q, 1,000 joules, and we want to know which will have the smallest change in temperature. Well, so this is just sort of the opposite case. If I want to keep the temperature the same, that will work when I have a larger CS. The bigger this number is, the smaller the change in temperature that I'll have. So high heat capacity means the temperature won't change very much for a given amount of heat that's added. These variables at a fixed amount of heat are inversely related, we'd say here. You can see that if we solve the equation for delta T by dividing both sides by MCS, we get Q over MCS is equal to delta T. And that, again, sort of shows you that the larger CS is, the smaller the change in temperature is, because that's on the bottom. And so here, then the substance is H2O. That's what will change the temperature the least, because it has that largest heat capacity. So H2O is the substance. And again, we can just plug in here. We already solved the equation, so we'll just plug in 1,000 joules over the mass 100 grams times 4.184 joules per gram degree Celsius. That works out to a change in temperature of 2.39 degrees Celsius. I don't know, I guess maybe 2.4 degrees Celsius to two significant figures. Okay, so this gets into sort of the conceptual meaning of entropy. Remember, entropy is represented by that letter S. So this is S in your tables. And entropy, again, is that measure of sort of disorder or randomness. It's really related to how many different possible places are there for sort of each of the molecules in your sample. How many different ways can you arrange them? And so the key fact for chemistry here is that gases have much greater entropy than solids or liquids. So the solids have the lowest entropy, liquids have somewhat more, but much greater than all of them are gases. And so the meaning of that is that since gases' entropy here is so much bigger than solids and liquids, to see whether a reaction is going to have a positive or negative change in entropy, we can just look at the change in the moles of gases. The more moles of gas, the higher the entropy. And since any of our delta, this is delta S for this reaction, is products minus reactants, if the products have more moles of gas, they'll have a higher entropy and delta S will be positive. If the reactants have more moles of gas, the reactants entropy will be larger and delta S will be negative. So that's sort of how we go through this. If we look at our first one, we're making a mole of oxygen gas. And so that means we have a higher entropy in the products. Products minus reactants will be positive, and delta S will be plus in that case. In the second case, we have 4 moles of gas as reactants, 2 moles of gas as products, and so the reactants will have more entropy. And again, then that means, based on our equation, if the reactants have more entropy, delta S will be negative. In the second case here, you can see we have 2 moles of gas on each side, both. And so in that case, we don't really have any strong preference for one side or the other. Probably the change in S is going to be pretty close to 0. So probably about 0 change in entropy for this reaction. So for this question, the two factors are the same. First, the same as before. The entropy for the different states of matter. Solids, all the atoms are sort of locked in place and don't have very many places they can move around to, so those have the lowest entropy. Again, entropy is that measure of how many different places are there for each of the atoms to go, how many different arrangements could you possibly have. So solids have the smallest because every atom is sort of locked in a fixed position in that crystalline lattice. Liquids, when you think about a liquid, now those atoms can start to jiggle around a little bit more, so they have a little bit more entropy, and that's because they're sort of jiggling about with a little bit of motion, and they can sort of slip past each other. In the gas phase, now, of course, we have huge amounts of many different arrangements. The gas molecules can fly all about our entire container, and so they have many, many possible arrangements, and they have much higher entropy. The second factor that we consider is temperature. If we think about the temperature, at absolute 0, again, all the atoms are sort of fixed in place, and there's only one way to arrange them. There's no motion of the atoms that gives each of them different places to go. So at 0 Kelvin, S is equal to 0. And as you raise the temperature, you get more and more entropy because the atoms start to move a little bit to, this is sort of low temp. And then at a very high temp, you have, much more motion and therefore much more entropy. So that's the basic idea here. So pretty easy conceptually here. Liquid versus solid. The liquid has higher entropy, higher temperature, again, for the same state of matter. The higher the temperature, the higher the entropy. Again, this is a liquid versus a gas. Gases all have much higher entropy than solids and liquids. Okay, so in this case, we're supposed to determine the delta G. Remember, that's the free energy, or the Gibbs energy, Gibbs free energy. That's what's going to determine whether a reaction proceeds forwards or backwards. That's this key thermodynamic variable. So, and we normally report that in sort of kilojoules per mole. Or we could use joules per mole, but it's an energy, so it has units of energy there. What is delta G naught of this reaction? Well, we're given delta H naught, and remember the key equation, the way we sort of defined this in lecture, was delta G is equal to delta H minus T delta S. And so we're given delta H, we can plug that in, and we can get delta S from the provided data. Just like delta H, we can do that. It's just basically products minus reactants. In this case, our products here are just the H2O2, so that's 109.6. And the unit here, S has a bit of a weird unit, joules per mole Kelvin, minus the reactants are 1H2. and one O2. That's 130.7 for the H2, and this here is plus 205.2 for the O2, and that gives us delta S naught is equal to negative 226.3 joules per mole Kelvin. And now we can convert all of this to get delta G. Delta G will just plug into this equation. Remember though that my delta H is in kilojoules, and my delta G normally I write in kilojoules, so I'm just going to convert this from joules to kilojoules. This is negative 226 joules per mole Kelvin, and then I'm going to do a unit conversion times 1 kilojoule over 1,000 joules, so that's moving the decimal place 3 places to the left here, and that gives me 0.2263 kilojoules per mole Kelvin. That will let me plug into my equation and get delta G. So delta G then is negative 187.78, and my units now are going to match kilojoules per mole, minus my temperature here needs to be in Kelvin. So remember, Kelvin is 273 plus Celsius, so this is 298 Kelvin. So minus 298 Kelvin times my negative 0.2263 kilojoules per mole Kelvin. And when I plug that in my calculator, I get negative 120.3 kilojoules per mole is my delta G for this reaction. Then for part B, is this reaction spontaneous? Well, remember that a negative delta G means the reaction is spontaneous. So yes, the reaction is spontaneous in that forward direction because delta G naught is negative. So at standard conditions, this reaction will proceed towards products. Okay, so this is basically a calorimetry question. We're going to burn some H2 gas, and the heat absorbed or released, remember, is related to the enthalpy or the heat of the reaction and the moles that we use. So in this case, we're using 2 grams of H2. We want to know how much heat is absorbed or released. So this is really just a stoichiometry question. So we can start from the grams of given, convert that to the moles of given, go from there to the heat using the delta H. So 2.0 grams H2 times, now we need the molar mass to do this conversion. So the molar mass here is 2.02 grams is equal to 1 mole. So I have grams, I want to get to moles, so times 1 mole over 2.02 grams times, now the conversion between moles and heat is now giving by the stoichiometry of the reaction. So I have 2 coefficient for H2. For every 2 moles of H2 I burn, I have negative 483.6 kilojoules of heat. Remember, the negative sign there means that that's heat released. So this is an exothermic reaction. So that unit conversion, I want to get to heat, so I'm going to put that on top. So I could put the negative in there. You know, the negative means released. I'll leave the negative in there, but you should sort of just know what that means in terms of exothermic or endothermic. So 483.6 kilojoules. And then I need my 2 coefficient on the bottom. So 2H2 there on the bottom. And that's going to give me the amount of heat that's, in this case, released. That's what that negative sign is going to tell me. So if I go into my calculator and do 2 divided by 2.02 times negative 483.6 divided by 2, that gives me negative 239.4 kilojoules of heat. So that's 239.4 kilojoules of heat released. Now we want to think about where is all of that heat going. In this case, I'm doing the reaction in a calorimeter. So maybe I have my H2 sample that burned, my H2 and O2 together right here. And then surrounding that is this big sort of vat of water, a couple of liters of water here. And remember, what was happening here was that this was an exothermic reaction. It's a combustion reaction. This was heat being transferred from the reaction to the surrounding water. So this is heat released, and the heat was transferred to the water. That's going to make the water warmer. We did a combustion reaction. So even though this heat here was negative, when we think about the heat, it was left the reaction, but it went into the water. So when I go to do this, I'm going to use my standard equation, Q heat is equal to mCs delta T. But now this Q is the Q for the water, so this is a positive Q. Again, exothermic reaction, heat released. We know the temperature of the water has to increase, so always think about that when you're going through these questions. So this is 239.4 kilojoules, and I'm going to need to convert that to joules to make it match my other side. So that's times 1,000 joules per kilojoule. That gives me just add 3 zeros on it, 239,400 joules is equal to 1,950 grams times 4.184, the heat capacity, joules per gram Kelvin, times my delta T. That's what I'm going to solve for. So when we multiply this out on the right-hand side, we get 8158.8 times delta T, and then divide both sides by that 8158.8 to get delta T by itself. Go through and do that, I get a change in temperature of 29.3 degrees Celsius, and therefore the final water temperature is just the initial 20 degrees Celsius plus the change 29.3 degrees Celsius gives me 49.3 degrees Celsius is the final temperature of the water. Again, the main issue people have is the signs here. So this is a positive heat transferred to the water.